For today's quiz, we're going to be talking about a car and a truck. They're both barreling down the highway. There's a sign that says, "Bridge out ahead." They both need to stop before they plunge over the cliff. So, the question is, if these two vehicles have the same momentum, which would require more force to stop them? This is what the quiz looks like. As always, please write your explanation, any math that you might happen to be doing, and then rate how confident you are in your answer. All right, let's go through the explanation together. There's a bunch of different ways that we can approach this problem. But in this case, we already know something about momentum, and that was a hint. So, if I have a small car and a large truck, here we have a cliff that they don't want to go over, so they're going to end up braking in some distance. And notice the distance is going to be the same for both of them. If they have the same momentum, we know that if a truck has a very large mass, so I'll put a large M in for that vehicle, this is going to end up having a very small m. In order to have the same momentum, this vehicle right here is going to end up having a very large velocity, where this truck is going to end up having a very small velocity. It's the only way that we can get them to both have the same amount of momentum. So one of the ways that we can solve this particular problem is, we already have the momentum, but we can use the work-energy theorem. And the work-energy theorem is a wonderful tool. We could say that work equals the change in kinetic energy. And the kinetic energy is going to be ½ mv squared. If we have ½ mv squared, we know that this vehicle is going to end up going faster, but a smaller mass. This is a bigger vehicle with a smaller velocity. If we end up working this a little bit further, we can say work is equal to change in anything is simply the final minus the initial. So I could say kinetic energy final minus the kinetic energy initial. Both of the vehicles here are going to have a velocity equal to 0. So that velocity equals 0, and that velocity equals 0 for their final. We can essentially say they're both going to be 0. We don't need to worry about that. So the work is equal to the minus kinetic energy. So we just really need to know about their kinetic energy initial. The reason why this is going to work out perfectly is because inside that work we have two values. We could say where work is also a force parallel times the distance. And because the distance is the same for each vehicle, we can now bring in force, and that's what we're looking for. So I'm going to put that in here. We have a force parallel times the distance equals our minus kinetic energy. And remember, the distance is essentially the same for both, so we could say that the force parallel is equal to, or I should say proportional to the kinetic energy initial. And remember, we had a negative over there I could take to the other side, and we know that our force is going to be in that direction. So right away, we know that all we need to figure out is which of these vehicles had more kinetic energy. If the kinetic energy is greater, the force is greater. Over here, we can look at this again, and maybe we can even just use some simple numbers to put in here. Let's pretend that we have a model so that we're not endangering real people and real vehicles being damaged. Maybe we'll make them model cars. And we'll make this 1 kilogram. So we'll say this is 1 kilogram, and this is 100 meters per second. It's kind of an absurd value because that's really fast, but for our purposes it'll work. And in this case, for the truck, we could say 1 meter per second. And let's make this, to have the same amount of momentum, we'd have to have 100 kilograms. I now have my mass, my velocity, and I can put it in for my kinetic energy for each of these. Let's do that quickly. So in this case, I could say our kinetic energy is going to be 1/2 our mass, which is going to be 1 kilogram, times our velocity, 100 meters per second. But that's going to be squared. And I think I already know the answer, because when I have a big number and I square it, it's going to be really big. So in this case, 100 squared would be 10,000. That 1 doesn't change anything. And then divide that in half. So that would be 5,000. On the other hand, the truck will do the same exact formula up here, and we would say this is going to be 1/2 100 kilograms times 1 meter per second, and then I square that. 1 squared is still 1, 100, and then divide it in half, and that's simply going to be 50 joules. So the car is going to require much more force to stop than this truck, which is going much slower. A bit counterintuitive, but interesting nonetheless. And remember, we could use any numbers that we'd like. If you'd like to put the numbers that are more accurate for a car, maybe 2,000 kilograms or 1,000 kilograms and so on, you could do that. Either way, the answer is the same. So that's your explanation for this quick quiz. All right, let's examine a little bit of student thinking on this problem. The reason why this is such an interesting quiz is because we're tapping into the students' intuitive notion of momentum. Momentum is really easy. It's just masses and velocities. However, the work energy theorem is a little bit less intuitive. And one of the interesting things about momentum is how many problems it can solve, but not all of them. So we have two great ideas that the students often forget to mix. We have momentum, and we also have energy. We also have Newton's laws. Momentum is wonderful for simplifying things. However, often we need to use both, and when we need to incorporate Newton's laws, the key is whenever we're talking about work, work relates to energy. Work also relates to forces and distances. Forces allow us to start thinking about Newton's laws. So it's a confluence of all your tools together that allow you to solve really kind of interesting problems and sometimes surprising. All right, that's how students sometimes think about this.